In this video, we'll define velocity, acceleration, and jerk. All of those things in terms of some position function. So we've got S of t. It represents whatever it represents. Maybe just to have a concrete example, we'll let S of t be a height function representing the height of a falling object. Maybe S of t equals 10 minus 4.9 t squared, where t is the number of seconds this object has been falling, and S of t, the position function, is the height in meters. So we've done a few examples by now with a falling object. And at this point, it should be pretty clear to us that the velocity of the object is gotten by taking the derivative of the position function. And in addition to, I hope, being intuitively sound, remember that the derivative is the rate of change. So the derivative of this is telling us how fast the height is changing, which is just a convoluted way of asking how fast the object is falling. But we can look at units as well. What are the units of the derivative of the position function? Well, the units of height are meters. The units of time are seconds. So the units of this derivative are meters per second. That is, in fact, a velocity. Velocity can be a positive or negative. You've got a position function defined in terms of a number line. You're measuring position from some zero. In this case, 0 represents the ground, and you've got a positive direction and a negative direction. So the sign of the velocity tells you which direction we're moving in. In this example, we're going down towards the ground. So we're moving in the negative direction. That should be reflected in a negative velocity. And if we take this derivative, we find that the velocity is negative 9.8 t meters per second. So yes, for any positive time, this velocity is negative. What if we're not interested in direction? What if we just want to know how fast the object's moving? Well, the speed of the object is the absolute value of the velocity. And traditionally, position function is s, velocity is t. Speed doesn't really seem to have a standard letter associated with it. We certainly can't use s because we've already used s for position. But moving on. So this provides us, this example provides us with a good concrete application of the second derivative. You see that I reproduced the higher order derivative notes for this unit. Acceleration of an object is what? Well, it's how the velocity is changing. Is the velocity increasing? Is it decreasing? What's happening to it? And if we want to know how something's changing, that's a question of derivatives. So the acceleration tells us how the velocity is changing. The velocity, in turn, is telling us how position is changing. So this is the derivative of a derivative. It's the first derivative of the velocity, the second derivative of the position function. Continuing to look at our falling object, we found its velocity to be negative 9.8 t. The derivative of negative 9.8 t is negative 9.8. Our meters, sorry, our units are what here? The units of the velocity were meters per second. The unit of time is given in seconds. So meters per second, which is often written meters per second squared. It's a little sloppy, but if you think of S as a variable, you can multiply numerator and denominator here by S and get to this. One more definition. Position, velocity, and acceleration are pretty common, day-to-day concepts outside of a calculus class. You'll still have heard of them. You may not be used to thinking of the jerk in the same way, but this does have some intuition behind it, because even if you've never thought of jerk as something that can be numerically measured, you probably have an intuitive idea of what it means if a car journey, for example, is jerky. If you're getting thrown around in your seat, it's because there's a high jerk. And the jerk is the derivative of the acceleration, which makes it the second derivative of the velocity, which makes it the third derivative of the position function. Continuing onwards with our falling object example, this is the acceleration, negative 9.8. The derivative of a constant function is 0. So that corresponds to our intuition that falling is not a jerky process. If I drop something, it falls smoothly.